Hello, I'm back with this frequency counter, and the plan is to do another modification on it. Since I've now got the rubidium reference, for anyone that saw the video last time on this frequency counter where I added the 3 gig DIY 3 gig option, I tried to calibrate this thing and the trimmer at the back just broke up. The internal oscillator is absolutely terrible, and now I've got a good reference. If you just take a look at what's being read here, this is coming off of that rubidium standard, and it's 940 or 939 cycles out at 10 megahertz, which is absolutely appalling for a good bit of kit. So when I was working on that counter, what I decided to do was measure up and find the space and have a look at the oven control crystal oscillator option. I did have a scout around to see if I could get any easy enough. They just weren't easy to get. They weren't really around, and the ones that were around were quite expensive. So I thought, I looked at the schematics and thought, a variation of that could be built quite easily. So I measured up and designed a board, and I received some just recently, so the goal today is to try and build that board and fit it. Now, I will go through the schematic in a second, but that's the board. It's really simple. The one thing that I did decide to do when I was laying this out was I've got a whole selection of different oven-controlled oscillators of various sizes. And also I thought, given there's such a really terrible oscillator in here, quite a cheap option is a TCXO, which is something like that, 10 megahertz TCXO, which wouldn't benefit from the auto calibration capability, but it certainly could be used as quite a low cost option. So what I've done is I laid the board out. If you have a look at the footprint here, if I can see this, and the various footprints here supporting the various elements. So I made a couple of minor errors on the layout. Didn't quite get the hole sizes right, so the components fit, but they're tight. Also, what I found with these two, for example, they're the same footprint, made by the same company, Isotech. Give me a second. Isotemp, sorry, and one of the things I found when I used the first one, which is someone actually lent this to me so I could get the footprint. When I used that one, that's a 5 volt device, and this one actually I got hold of on eBay, and actually this is a 12 volt device. So one of the errors I made, although it can support the footprint, this one is only assuming a 5 volt, and so I can't run the 12 volts on it unless I do a bodge. There was one other tracking error, which I'll not a tracking error. It was just a lazy design error on my part. Very easily fixed, and I don't think I'm going to bother getting the boards redone. Although if anyone does want them, and I might get some more made. But anyway, I'll go into that later on. Anyway, the idea is it's a universal OCXO board, and while it's designed specifically for that HP counter, it probably could be used in other things. But really, it's just a board with a little bit of power supply filtering. What's I guess different about this, and why not just put the OCXO straight in there and hardwire it in, is one of the components on it, and we'll go through a circuit, is an analog to digital, a digital to analog converter. And one of the really nice things about this frequency counter, once it's working, once this is in, what we should be able to do is just from the front menu, feed in 10 megahertz, a known good reference, tell it to calibrate itself, and it should calibrate itself. So that's what we're going to do. Anyway, what I'll do now is, so just before I build this up, I'll just get the schematic, and I'll walk you through the schematic very quickly, and we can talk about how it works. Okay, see you in a second. Okay, so the schematic's pretty simple. This is essentially functionally block diagram level, actually almost electrically as well. It's almost identical to what's in the original option from HP. There are a couple of minor differences, but it's just really around power supply and so on. So nothing too onerous. It was a pretty straightforward circuit. The heart of this, so we'll start here, is this digital to analog converter. It's an AD7243. It's an obsolete part now, and actually analog do recommend a newer device, and I was going to look at using that newer device, but when I looked at it, the SPI serial protocol for loading this value into this 12-bit DAC, actually the protocol is different, so I would have had to, I don't know, put a pick in there or something, and I just thought you can still source these chips. They're not that easy to find, but they're definitely around. So I decided just I'm not planning to mass produce this thing or anything. So I decided just to get the chip and stick with it, just to save doing the protocol conversion. Anyway, so it's basically there's a SPI interface in to program this DAC. There's the various power supplies, just some simple filtering around here. There's a 5-volt reference, and that's quite important because that's stable, because that 5-volt reference is used to control the oscillator, and we'll go through that in a second. The other part that's notable on here is this LM361, and what this is the differential output high-speed comparator. So assuming the oscillator is providing a sine wave, some do and some don't, what this basically does is this cleans up that that signal and turns it into a square wave, and puts the what the counter seems to require is a clock and a clock inverted signal. And the original schematic had a very small inductor and a very small resistor, so I've put those in place as well. So that's the whole circuit. There's nothing to it. So the ADC is the DAC is set up from the 5-volt reference, and the output of the DAC, the voltage output, goes to what would be what they either term the voltage control or the frequency control pin of the OCXO. So if we talk about the OCXOs for a second, something like this is basically is an oven. So you power the oven. That's typically, this one happens to be 24 volts, although it does run on 12 volts because I checked it, to see if it would. And then it's got an oscillator supply, an oscillator output, and then a voltage control. And basically these things are meant to be within spec, to 10 to the power of 9, 10 to the power of 10, within a couple of parts per million. And in fact, the OCX I'm going to use, which is it's made by, which one is it? It's a siliquartz part. The voltage control trims it to plus or minus 0.3 parts per million. So it's a very, very narrow window, but it is there to allow you to trim and tune the voltage. This one, for example, has, if I open this, there's a trimmer inside, so you can actually trim these off. And these all have different variations, but the basic structure is the same. Power the oscillator, power the oven, which may or may not be on separate pins, depending on the device, and then you've got a voltage control. You can either leave it open circuit and then it'll just run at its frequency, or you can tune it. And the way it's done inside the HP here for the automatic calibration is it uses this ADC to derive that voltage. Now, when I tracked this board, I actually tracked it and wired this this DAC exactly the same as it was wired in the original circuit. And if you look at the data sheet of this DAC, which we'll go into, we can look at in a second, it has 3 modes of operation. The voltage control, the voltage output, of the DAC can be plus or minus 5, or 0 to 10 volts, or I think 0 to 5 as well. So depending on how you configure it, and I think this is configured for plus or minus 5. And one of the problems with that is the OCXO that I happen to use needs a 0 to 10 volts voltage control. So we'll look at that in a second, because originally when I put this together, it didn't actually. In fact, here, this is the one I built. So you can see it there. Let's see if we can get some focus. And when I put this together originally, you can see there's a little bit of a bodge wire there, and I'll just show you what that is and what I should have done with this board. And I feel really compelled to go and get these made again, but it's such a small mod, as I say. I'm probably not going to bother because I've got a few boards here. But basically, the VREF pin here, I've got it hardwired to the 5-volt reference, and actually you need to be able to put that to analog ground or 5 volts or the V out, depending on the voltage output configuration. So ideally there should have been a couple of 0 ohm resistors, and I could have just soldered in place the right one, because each one of these OCXOs, they have different voltage requirements. And funny enough, when I laid out this board, it was, I don't know, I was probably just being a bit lazy, but I did think about that. I thought, that'll be okay. I'll sort it'll be fine. But of course, it wasn't. Anyway, we'll go into that. And the reason why I wanted to go through that is I think it'll be interesting to see once we fit this, how that counter calibrates itself and what it does when it can't calibrate. And we can see that and look at it on the scope and so on and see the effects. So that's what I'm saying. Everything else is very straightforward, self-explanatory. These are just the 4 footprints that I've used, and they're all wired accordingly. This datum one takes, as I said before, runs on 24 volts. So I've put a small socket footprint on here, so you can either link that out or you can provide an external 24 volt supply. Someone also suggested that I put a couple of SMA footprints, so if you don't have an OCXO but that fits on here, but you want to use it for something else, then practically you could put a couple of SMA sockets on here, and you've got voltage control and frequency in. Right, so I think what I'll do now is take this thing apart and have a look at fitting this, and then we can do the initial calibration. I've got the wire. The bodge wire wired so it was in the original state as per the original board layout, and we'll go through the actual calibration routine. You can see the effects of what happened. So let me just get ready. I'll take this apart and get this fitted, get the bench set up, and then we'll come back. Okay, so I've got this out on the bench. I'm just going to work on it like that because, as I say, we know this doesn't calibrate. And the first thing I was going to do, so it's really simple. It's just a simple single ribbon cable into the main board here in that expansion socket, and then into the board here. Now the board, as I've laid out, we'll go through this later once it's working, but that'll basically mount in there. And so you can see there's plenty of room and so on. Now, these oven controlled oscillators, they take quite a while, I don't know, 30 to 60 minutes probably to get to a working temperature, and that's one of the downsides of them. So although I'll have this in this board, the likelihood is I'll also have this counter connected to the rubidium reference, because that actually takes just a couple of minutes to get going. So what we really have to do is we have to let this warm up and let it stabilize, and the way I'm going to do that, or the way I suggest to do that, is the way I've got this counter wired at the moment. 10 megahertz in from the rubidium reference on the front. We've got the output here going to the oscilloscope. So the 10 megahertz reference is on channel 1. I'll just show you up here. Just move the camera. I don't know how well that's going to. Let's see if I can tune that so you can see it. So I've got the, this is the rubidium reference, this is the reference output on the counter, and so what we'd expect is when we turn the counter on, the internal reference, i.e. this new OCXO that I've fitted, and the external reference will be wildly out, and we should see exactly that. So now what you need to do is, this OCXO should get pretty close to that on its own, regardless of the cal range that's on it. So we just have to wait and let that warm up, so we can actually see both traces, and we'll see both sine waves, and you should just see it run one way or the other. So yeah, that's before we even attempt to calibrate it. That's what we should do. But just before we go through that, I'll bring the camera back down here again. What I thought I would do is, yeah, just before we do that, I'm going to disconnect this and just show you how to get into the calibration menu of this counter, and then show you the calibration routines. So hopefully it's not too unwatchable on the. Let's just turn it over. It's easy enough. Okay, so to calibrate these things, all you need to do is press and hold the scale and offset button while you power it on. And it'll come up with cal unsecure or secured. If it comes up secured, you've got to enter a code. We don't need to, just press scale and cal again, and then go through the menu. And you can see that the only options I get: offset 1, offset 2, gain 1, gain 2, and TI quick, TI fine. So I don't get the OCXO option. Now if I power that down, once the option's fitted, it should detect that it's there. And I should have the option to calibrate it. So now if we've got option 1, option 2, gain 1, gain 2, TI quick, TI fine, and cal Timebase, there it is there. And once you press enter on that, as you can see, it'll tell you to supply a 10 megahertz reference to channel 1. And then press enter, and it'll go away and it'll try and calibrate. Now that'll probably sit there for 2 or 3 minutes, so I won't video all of that, but that's essentially what it'll try and do. Now clearly, you shouldn't try and do this when your OCXO, when your oscillator is unstable. So you're meant to leave these things, and I don't know what the recommended amount of time is. I suspect probably 2 hours. So I'm gonna leave this on now. I'm gonna leave this on and let that OCXO get up to temperature, and then I'll come back on camera. I'll come back on camera once this is filled, actually, and I'll show you the what the failure message looks like. Okay, so you can see that what it's saying is time-based calibration failed. Excuse me. I can do that as many times as I want now. Just press enter again, and it'll ask me to supply 10 meg, and it'll keep on doing that. So it's quite an easy cycle to get into once you're in there. I thought what I'll also do is just reposition the camera. Just before I do, what I'm going to do is I'm going to put the scope probe here, DC levels on the voltage control, and we can have a look at the scope and see what it on the scope and see what it actually does while it's trying to calibrate. I can get this lighting right. The lighting's, I haven't quite got this lighting right, so sorry about this. Okay, so I'll put it in on channel 2, and I know it's not going to go negative. So this is on channel 2 at 2 volts of division. Let's just set that at 1 volt of division. So so that's if you mark that as the 0 point there, and I'm just going to, I can't remember which one's the voltage control now. Okay, so that's where it's currently sitting while it's waiting for me to press enter. So what I'm going to do now is press enter, which initiates the calibration routine. And this is the voltage control line. This is effectively the output of the DAC on that board. So as I press enter, I think it sits there for a second or two while it's counting the actual input, and then you should see it starts to try and adjust the frequency. There you go. So it's just jumped up. And you can see there it's just jumping up in steps. So it's obviously jumping up, then it's counting, and it's going, no, still low, jumping up, counting, so still low, and jumping up, counting, still low, and then eventually it gives up and brings the voltage control back down to where it fails. There we go, so around about the midway point. And now that's the reason why that's like that is because the configuration at the moment, I think what it does is it defaults to the midway point on the ADC, which would make sense. And its default configuration is, as far as the original implementation on the HP extension module, is it actually swings plus or minus 5 volts. So you can see it at 1 volts a division. It's set, but the output I'm getting here for the entire range is 0 to 5 volts because the configuration is wrong, and that needs to be 0 to 10 volts. So what I'll do now is I'll do the modification on the OCXO board, and then I'll also let it warm up. Okay, so the scope, you can see now the OCXO. I've done the calibration mod, and the OCXO is warming up. And what we want to do is let that stabilize. That's the most important thing. Now I have tried to calibrate this before, and so it's probably going to be pretty close. You can see at the moment it's running a little bit slower. The OCXO is running a little bit slower than the rubidium standard, and it's very rapidly reaching temperature, so it's getting to the point where it's going to stabilize. I suspect it will probably run the other way. You really need to leave this on for about an hour, which is what I'm going to do now, in order to there you go, it's warmed up and it's started to run the other way. What we're looking for is to get it to the point, it doesn't matter what frequency it's at, but we just need to make sure it's stable. And the way to do that, I'll just come away from the scope because we know we're pretty close there now. So the way to do that is when you're looking at the counter, is we just need to leave that run to the point where those numbers no longer change. They should be sitting there. You can see that although it's jumping around a little bit, it is eventually, I think it might be getting close to stabilizing now. Anyway, I'm going to go away and just leave that for a little while, and we'll come back once we're pretty sure it's stable. Okay, I brought a scope here just so we can see everything in context. I've got it currently on a calibration cycle. You can see that it's running a bit low, and it's actually, this is just as we spoke there, it's just past its calibration. It does take a little while to get to that, and you know, I've been through a few calibration cycles with this meter now, and I can tell you that the software in it is not great. If you look at this, it's saying here calibration passed, so it's passed its calibration. It's happy, it's probably within spec, but you can see clearly that's not running. I know it can do better than that. And the point is its calibration cycles are actually random. So if we run this now and have a look at the measured frequency, you know, we're out by 82 tenths of one cycle. Sorry, 22 tenths of one cycle there or thereabouts. And that's not great. So what I'm going to do is I'm going to run it in, I'm going to just start another calibration cycle, and you'll see the results here. And this is a good way to check it. But obviously the point is when you're calibrating these things, it's definitely worth having a scope set up in this way, so you can see, because it's a very clear visual indication of how well the calibration's gone. So let me just run another calibration cycle, and then we can see how that performs. Unfortunately, you can't press enter. You have to wait for this silly message to complete. Okay, so I'll let that calibrate. Now you'll see that if you remember on the other scope, it stepped up the voltage. What you'll see is this. You'll see step changes in this. There you go. That just made a step change there. So what it does, it tries to find its window. Let's just see if we can see it do that. Once it finds its window, it'll probably go the other way a little bit, and then it should bring itself back in. Actually, it's done a pretty good job at finding that there. So that looks like it's still, there you go. So it's gone in the other direction now. So it's found its window, and now what it's going to do is basically, when you'll see this slowly trim to a known calibration point. And that there looks like I've done this a few times now. That looks like a pretty good calibration cycle. You can see that the two are locked. It's just playing around there. Maybe it's running just a little bit slow, but yeah. So that looks like a good calibration cycle. This should complete in a second, and then we can see what the results are. It does, and just so you know that when it's calibrating here, once it gets to that fine-tuning point, it does take quite a while. It sits there, and I presume it does count after count after count. Oh, there you go. So it's happy that it's passed now. So if we run the counter now and see what the output is, I'm expecting that to be a pretty good measure of the rubidium. And there you are. That's pretty close. I'm pretty chuffed with that. 10 megahertz and 2 decimal places. That it's just on the borderline. It can be gotten a little bit better. Obviously, there'll be a little bit of drift. Yeah, that's pretty good. I'm pretty pleased with that. I might run 1 or 2 more calibration cycles and just get it spot on. Something else I observed when I was playing about with this, which I thought was quite strange, or not quite strange, but probably just worth highlighting, is that the orientation I'm presuming this is a gravity thing. It could be either gravity or magnetic. I haven't put too much effort into trying to find out. But if I pick up the OCXO board here, you can see it there. Well, actually that oscillator's quite hot. Let me just hold the board here. And if you look at the counter, when I change its orientation, it's at the moment it's sitting vertical. So if you bring it round, you can see the vertical plane there. And observe what happens when I actually rotate this. It actually has an impact on the frequency. Now I thought, oh, maybe there's noise or something going on there. And if I bring it right the way around, so it's 180 degrees vertical, you can see it's lost 3/100ths of one cycle. And what's fascinating about that, or what I thought was fascinating about that, is it's actually highly repeatable. So if you just bring it back, it comes back to exactly the same frequency it was at before. And I don't know, maybe that, who knows, that maybe that's how accelerometers work. Perhaps not, but perhaps it could be used. Or quite an interesting characteristic of these things. So it's obviously important that when you calibrate them with that in mind. You can see the effect there. But what is amazing is how repeatable it is. Don't know what it is. If anyone's got any ideas, if anyone knows, I'd love to hear the comments. As I say, it's either gravitational pull or magnetic. I did try waving big bits of metal around this thing, but that didn't seem to make any difference. So it seems more like gravity than magnetic, but who knows? Anyway, I'd say that's a pretty good end result. It's a real shame about that little bodge wire, but I don't think it's worth changing the board just for the purpose of my counter at least. I have actually done 2 revisions of this board since in terms of layout, and I'm not sure. I might get some made and make some of these things for people that might want them. I don't know. I'll have a think about it. But the end result is pretty good. So now I'm going to see if it all physically fits together and maintains its calibration once I close the lid. Okay, because I've got the power switch modification here. I was actually using one of the mountings that's designed for the OCXO board. So I've just used a hex nut spacer here with a thread on the end, just because it's what I've got to hand. And then on the other 2 mounting points, I've just got these spacers and these screws going through. So I just thought I'd show that before I put it back together. Okay, so there's the expansion board. Sorry, the OCXO board finished. Let me just see if I can fit it and actually in the counter there. You can see. Get these right angles here. So you can see it's I've got slight length differences because of that mod and the different spacers I've used, but other than that, it fits perfectly. Everything lines up. Yeah, it's really good. It's nice and tidy. So let's just power it up and see if it actually still works. Now, of course, the OCXO will be a little bit cooler now, so that's going to have to warm up. Let's just give that a couple of minutes and see if it gets back to. It's only been off about 10 minutes, so let's see if that gets back to its 10 megahertz reading. That's been running for about 10 minutes now, so the OCXO has got back to its working temperature, and as you can see, it's just on the borderline. It'll probably warm up a little bit more than that, and get back to where it was. So I'm actually pretty chuffed with that. That's I think I'll put that back together now. Actually, you know what? I'll just as a reference, it might be worth looking at the other counter I've got, the Raycor Dana, because that's been really reliable up until now. Now I think this is a much better counter. And certainly with the modifications it's had to it, it certainly is now. But let me just get that down and we'll have a quick look at that in parallel with this. Okay, so there's the 2 counters running side by side. You can see this is about 1 cycle out, this counter here, in comparison to that. And obviously I'm feeding both with the rubidium from the rubidium frequency reference there. So this counter, is really good. It's really stable as well. That's what I've noticed since I've had that rubidium stand. This is actually, once it's warmed up and it's got to temperature, it actually works really, really well. So it must have an OCXO in here, or possibly a TCXO. I'm not sure. I'll have to open it up. Now this counter has actually got a bit of a fault on it. Sometimes, I'm not sure if I'll be able to replicate it. Sometimes it hangs, and it doesn't work. And then normally a tap on the side or something gets it going. And I didn't want to mess with this because although it's got that fault, it was still very usable. But now I've got this counter. Obviously, I can do a bit more with this, so I'll probably take it apart and see if we can repair it. The other thing is these buttons on these counters are really horrible, and they just need replacing. They're just, you have to press them really hard. They've lost all their tactile feel, and it's a kind of well-known problem on these counters, so it needs to be stripped down. But now I've got a good working counter. I've got the opportunity to take that one apart. All right, that's it. I think I'm done with this mod. I'm really pleased with that now. I've just put that back together, and it's up on the bench, and I can now use it. I would say that it's the internal oscillator on that, the one that comes with it, really isn't worth the. It's terrible. It's absolutely. You've seen how far out it was when I tried to trim it. I guess because of its age, but even so, the type of component being used there. The ceramic trimmer just broke up into a million pieces, just really poor, and unfortunately it makes the counter next to useless. Can't rely on it. Wasn't stable, wouldn't give you accurate readings, that kind of stuff. With this modification, it makes a huge difference. So for the cost of doing the modification, I think from my point of view, I found it quite interesting doing it, creating the board, and messing about with the calibration circuitry and so on. Definitely worth the trouble. It's a really good upgrade to that counter, and I would highly recommend anyone that's got one of these counters, if you don't have some kind of higher stability oscillator option in there, you should get one or put one in. I don't know, I might make a few of these, so I've done 3, I think this is on the first one, I've done 3 revisions to this board, just general improvements and so on and so forth. So in terms of the design, I haven't got them made, and I feel a bit compelled to go and get some made. So I don't know, maybe I'll do that and experiment with some of the other oscillators. But anyway, regardless of what I would definitely recommend, if you've got one of those counters, you should do something with it if you want it to be a reliable and dependable piece of kit. Okay, well I hope you found that video interesting. If you did, please give it a thumbs up, and I will catch you next time.